Again, welcome in everyone. Appreciate you guys taking the time here on a Monday night to join us and Jesse as he's covering all things 1080 motion. My name is Nick Simi. I'm a performance physical therapist and athletic trainer for the Charlotte Hornets, and I'm also here with co-host Daniel Yu. Daniel.
Yep, my name is Daniel Yu, co-host with Nick. I'm a sports scientist and strength coach in the NBA. Just really excited to have Jesse here with us today.
And we have Jesse, who needs no introduction. He has a great following, as we can see here on all the people that were interested in his webinar. He is currently the director of performance science for 1080 Motion out on the West Coast. Previously, he's held roles as director of performance and sports science in the NHL with the Pittsburgh Penguins and also the Sacramento Kings. He has his Masters of High Performance Sport from Australian Catholic University, and his undergrad in Bond University. So without further ado, Jesse, the floor is yours. Oh, and then one more note too. As he goes, Jesse would invite you guys to ask questions. Throw those in the chat. Daniel and I will monitor those, and we'll take questions as we go. Thanks, Jesse.
Perfect. Well, first of all, thanks for the invite, guys. As I posted earlier, I think you guys are doing great work in the space of performance and sports science, especially around the CPS, of course, but external to that as well. I think you guys are really doing a lot to push everything forward. So let's get into it. I kind of want to talk today about, yes, the applications of 1080 motion, and by no means do I want this to be, salesy or pitchy in any respect, but having been an advocate of 1080 for a long time now, both as a user and now working for the company, I really do think that it certainly changed the way that I practice, particularly around the RTP and healthy athlete training standpoint. And I just wanted to share some of those reflections with you today. So we'll cover off a couple things, my personal closed loop process that I think 1080 can facilitate, but also some assessments, trainings, profiling, RTP, a little bit of tendon at the end as well. So first of all, Nick kind of touched on it, but my brief kind of journey so far, I always like to put this up just because you never know where a new connection will come from. So I always like to put this up, but started in Australia in the AFL, more of a student kind of research capacity, and then made the shift over to America into the collegiate space with the University of Louisville for just over a year. And then, as Nick said, spent a bit of time with the Kings, the Penguins, and now 1080 Motion. So just briefly touch on this because I think it's pertinent to some of the things I'll be talking about today. But these are kind of some of the series of 2 equipment that we have now at 1080 Motion. Predominantly, we'll be talking about the Sprint 2 unit, which is this one in the middle. That's kind of our most common tool, the one that you'll see out in the wild most commonly. And then the machine on the right is our new 1080 cable, which is more so designed for higher force movements, more gym-based, still a very versatile tool, but something we use more so in a gym environment. And then lastly, we have our quantum synchro unit, which I was very fortunate to have one at the Penguins. They're pretty synonymous throughout NHL organizations these days. There's some more and more popping up in NBA collegiate circles as well, but I will be spending most of my time talking about this machine here as well as the Sprint 2 unit. So if we get into it, I think it's always pertinent to start here with my process. And not only is this a personal philosophy of mine that I've kind of polished over time, but this is something that I think 1080 can also influence and facilitate the onboarding of 1080 throughout the kind of journey of adopting technology, but also maximizing its use. So I think when we close the loop, this is a closed loop process effectively. But first of all, we have to identify the qualities and the capacities that underpin either the injury, epidemiology, or the demands of the sport. Makes sense, right? We want to find what's pertinent to the sport. We want to assess that. And then we want to use where we can valid and reliable tests where possible. I understand, and I've been in that seat where sometimes what you want to assess or measure isn't necessarily within the literature or perhaps within S&C circles. So you have to kind of create your own, perform some in-house reliability testing, and go from there. So that assessment piece is critical. But then from there, what we have to do is we have to make sure we profile that information. And this is where I think there's been an explosion in data and in information, obviously, throughout the S&C environment and globally in other kind of neighboring industries. But we have to profile that information against whether it's internal benchmarks, norms in the research, professional opinion even, to identify where we need to spend our time and perhaps where we need to just maintain training residuals. From the profiling piece, obviously that must lead to some sort of prescription to identify those areas, and then we monitor those changes over time, and that closed loop process continues to flow and flow and flow. And this doesn't have to necessarily be, tests within the gym or tests on the court. This can be subjective testing. This can be manual muscle testing. For me and my approach, everything kind of flows through this, and it can happen on a very, very short period of time, minutes, hours, or this can be, a season, annual kind of prescription or annual process that can be undertaken as well. So when we talk about assessment and profiling, I think two of the key pieces that obviously start that process, there's a lot of things that 1080 can do. And there's a lot of things that the technology is known for. I think to keep it succinct and to keep it applicable, we're going to focus on primarily these things. So linear sprinting, predominantly acceleration. I'll spend a good amount of time on change of direction. And then to close up, we'll talk about RTP, some force diagnostics that I think are really applicable. And then a couple slides on tendon loading as well, that I think is quite an emerging topic when it comes to some of the resistance types that 1080 can afford. So first off, we'll start really simple, just a basic linear sprint. So we can see one of our logistics guys at the Swedish office, Leo, poor guy. He's one of the younger guys in the office. He's a soccer player. He is in hundreds of videos for us, recording videos for us. So thank you to Leo. But on the left-hand side here, we can see a very basic raw output of what the 1080 reads. So we can see on the y-axis, we have our speed. X-axis, we have position. You can see it's a 30-meter sprint that he's undertaken, and I've just laid on 5-meter splits. But this is generally speaking what we would see from an output standpoint for a raw speed trace for sprinting. So that's the assessment. Now, when we get into profiling, this is where we can start to get a little bit more sophisticated and a little bit more targeted with what we're trying to do. So we can see from that raw velocity trace, we have early acceleration, transition, and max velocity. You can call it late acceleration. There could be more phases. I kind of break it down just based on these 3 basic phases. But again, you can kind of use whatever demarcations you would like. And what we've done within the software now as well, with the excellent work that JB Marin and Pierre Samazino have been putting out for some time, is force velocity profiling. So we figured that, why not embed this within the software? We have a lot of users that really like using that information, using those outputs for profiling. So let's embed that within. So then we can go obviously with speed and distance and force, but we can also now look at force velocity profiling metrics, and I'll get into load velocity profiling as well. But all of these sit within that profiling bucket for us to be able to effectively determine where we should spend our time with a given athlete. So force velocity profiling, I'm sure you're all somewhat familiar with these curves and what they look like, but just as a quick reiteration, we model the speed curve based on a smooth line. We can see that on the left-hand side here. We have our raw step curve that we then fit that modeled speed curve to. And then from there, on the right-hand side, we have our force velocity profile with our power mapped on top of it as well. And there's been a lot of different research, a lot of different discussions on the back of this. Stu McMillan, the other day at one of our summits, he mentioned he's found some really cool correlations with some of these force velocity profiling metrics and just existing outputs. For example, he found in some of the football players, like big linemen, larger players, 250, 300 pounds plus, P-max, that max power, 90% correlation to 10-meter time. However, when you look at more of the position players, he found more of a 60% correlation. So we know maybe for the bigs, P-max is driven more so by force, maybe for the position players more so by velocity. So when we drop down or kind of branch off from P-max, we can then get our theoretical max force, F0, and our theoretical max velocity, V0. And those are plotted just down the bottom here as well. But where I think is some of the most potent profiling tools is the ratio of force values and the DRF. So ratio of force being a calculation based on how far and how fast that athlete moves within the first step. What is the orientation of that force? 34.9% is a pretty atrocious value. We want that to be as close to 50% or higher as possible to indicate greater projection and greater horizontal projection of that force rather than vertical straight out of the blocks. Then that number right beneath it, that's that DRF, in the decrease in the ratio of force. that's a value we want to be as low as possible. And that value kind of indicates how that force, kind of the trajectory of the force, how much that horizontal force decreases as we increase speed. So effectively, ratio of force, how much is being projected horizontally, decrease in the ratio of force, how can you sustain that horizontal force output throughout the first few steps. So now if we go down more of a prescription route, we can kind of break some of these down, and I've adapted a lot of these from some of our elite users, but there seems to be a couple buckets that we can pull from here and use those profiling metrics that we get from force velocity profiling to inform some of our practice. So if we look at orientation, RF max, as I mentioned, as well as projection, more as indicative of theoretical max force, how hard you can push out of the blocks. Some very useful prescription tools on the back of this might be some heavy resisted accelerations, some concentric strength, and a shorter focus. Makes sense given that with heavy resistance, we're obviously being forced or constrained into more of a horizontal projection type position. And as that's sustained throughout the run, whether it's 4, 5, 10 meters, we're maintaining more of that acceleration like mechanic and those shapes that we see in early acceleration. And then if we switch over here to more of the switching rhythm and the stiffness and rise, more indicative of late acceleration, getting towards max velocity mechanics, where we know the shapes and the kinetics of what sprinting looks like changes quite drastically. So I think on the back of that, the prescriptions that we should use are also need to be targeted towards those different qualities that we're trying to develop. So maybe slightly lighter load, something targeting more of a max power as opposed to a heavy force. We can work at more of a moderate to short focus when we're talking about switching and rhythm. And then as we get to that stiffness or the rise component, we can start to address DRF or use that decrease in ratio of force kind of as our profiling tool that we can then check back in on as we train and as we, over time, continue to sprint. So here's a couple of videos. I won't spend too much time on this. On the left-hand side there, we have Leo lining up with a heavy resisted sprint. And we can just see based on this is there's very little rise. He's maintaining that kind of horizontal, or sorry, that negative foot speed, striking right underneath or maybe a little bit behind his center of mass, focusing on projection and orienting his body forward and more horizontal. And now if we look on the right-hand side, we can see he's actually getting an assisted acceleration. So he's starting on the right-hand side and he's getting towed towards that 1080 machine. Something I think is an emerging topic with not only with 1080, but resisted and assisted sprinting in general is the impact of assistance on the acceleration. I think that within the next 3, 4, 5 years, there's going to be a lot more research and a lot more conversations around how assisted, not only sprinting for top speed, but how we can use assisted sprinting for acceleration. I think there's going to be a lot more conversation around that. So if we move on from force velocity profiling, excuse me, to load velocity profiling, this is something that I'm sure many coaches on the call here that you're familiar with in the gym. Load velocity profiling with trap bar jumps, mix it with the CMJ, load velocity profiling with medicine balls. This is effectively the exact same thing, but with sprinting. So we can see here 3 repetitions. We've got speed over distance. You can see our green repetition, that's a light 2 kilo resisted run, followed by a moderate 5 kilo resisted run, followed by a heavier 10 kilo resisted run. And this was done with a junior soccer player. I believe he was 14, 15 years old. So automatically we can see here that the speeds, the max speeds that were achieved at these 3 different loads are obviously different. Obviously, the heavier the load, the lighter the top speed. No questions there. But then what we can do within the software now, again, this is something that we've built in off the back of something we found that coaches desire or something that we found that coaches want within the software, is we can now plot that load velocity profile for sprinting. And not only can this be applied for sprinting, we can do this for any exercise. If you want to do a load velocity profile on single arm rows, on horizontal chops, on half kneeling press, it can be done with any exercise you wish. There just has to be somewhat of a decent demarcation of loads. So maybe creating a load velocity profile with 3 kilos, 4 kilos, 5 kilos, maybe won't be the most valid, but there's just going to be a nice spread of load there. And then what we also provide you with is some information related to how accurate that profile is. So we can see on the left-hand highlighted box there, we can see that there's the R-squared value, 0.991. For me, anything above 0.99 is acceptable. 0.985 I would also use as well. But we can achieve really high R-squared values, and I think we should strive to do that if we're going to use these for prescription, which I think is the ultimate goal here. And then with that, we also provide a velocity decrement table, or VDEC, which has become very popular with resisted sprint training as a way to individualize the load, or individualize the prescription, and also an incredibly excellent monitoring tool I've found in my experience as a coach as well. In that, if we create a load velocity profile in pre-season or in some point during the pre-season or the preparatory period, we can now know that if we want to target, say, a 50% velocity decrement, we know that our load is 9 kilograms. That will be put straight onto the machine. We don't have to worry about clicking that in manually. But the good part is the output, we're looking for, if we're looking at a 50% velocity decrement, would be 3.8 meters per second. So any repetition they perform that may be below 3.8, if we're looking at 3.4, 3.5, we know that there may be fatigue at play. There may be some maladaptation. Maybe we haven't touched on that for a while, that quality. Conversely, if they're starting to exceed that velocity decrement threshold of 3.8, they're starting to get to 4, 4.1, 4.2, we know that there may be adaptation taking place or an increased freshness. So it's just another way that whilst we're training, we can also be monitoring at the exact same time, which I think is become more than commonplace in the majority of sporting environments now. The testing is training, training is testing approach. And I stole this from Nick Grantham. He's at Newcastle United Football Club. I've linked his presentation down there. It's on YouTube. You can go watch that. But this is kind of how they've bucketed their resisted sprinting profiling, also resisted sprinting work. It's a little granular, so apologies for that. But they can see very similar. They've got bucket for projection, for switching, and for reactivity. For projection, they're using 50% velocity decrement runs, only 1 to 2 reps, so that microdosed approach that's also become quite common in sport. So we know that that's going to be a heavier load. We're going to be focusing more on force production. It's going to keep them in more of an acceleration type mechanic and pattern. And then we move to switching, so perhaps more synonymous with late acceleration or that transition phase, where we're using a slightly lower velocity decrement, so 30% run, so slightly lighter weight. And then as we get up to more reactivity, so perhaps getting closer to max velocity sprinting, an even lighter 15% velocity decrement. And again, the beauty of this being that even though those loads will be slightly different for each player, everyone is getting a similar stimulus in the sense that they're getting their own 50% velocity decrement load. So using this, it's a very accurate way and a very reliable way to ensure that each player is getting an adequate stimulus or an individualized stimulus. Because if we were to go out onto the field and we were to just put 10 kilos on, you might undershoot some, you might overshoot the others, and you might hit the nail on the head for some. But using this velocity decrement method, I find is a really good way to keep the stimulus synonymous across the entire group. Okay, let's get into some asymmetry. So what we're looking at here is another speed over position chart of 6-month post-ACL reconstruction, pro female soccer midfielder. It's a 3 kilogram run across 30 meters. So 3 kilograms is what we recommend the lightest load to be, as it maintains nice tension in the line. We don't get slack or what we call line sway, where you can see the lines really moving around, really impacts your data and you get a lot of artifacts out the back of that. But before I even move further, you can really start to see there's some funky stuff going on at around the 5 to 6 meter mark, around step 7 or 8. So early on, early acceleration up to 6 meters, this athlete looks pretty normal, I would say. That's a pretty common looking acceleration curve. We can see those peaks are starting to rise pretty reasonably. We can see that nice kind of curve as she's starting to accelerate. But then again, as we get to perhaps meter 6 or steps 6 or 7 or 8, we start to see some really interesting things occurring. And this is where I think we start talking about strategy. And, I kind of think of this akin to where we were with force plates 15, 20 years ago, is that, we went from jump mats where we got output. When it comes to sprinting, we had timing gates or have timing gates. But then we went to force plates and we could start to see in a CMJ, for example, we can look at impulses, force at zero, peak velocities, mean velocities, peak forces, all of these different metrics that we can use to describe the output and the strategy that describes the output. And I think that's where we're at now when it comes to motorized resistance and sprinting and change of direction, as we'll get into as well. We can start to now see phase level asymmetries. So again, early acceleration here looks reasonably normal, but as we get into that transition phase towards max V, we can start to see some asymmetries starting to pop up. So not only can we use this as a diagnostic tool, but we can also use this to then profile areas of development, which in RTP, incredibly useful, because we want to make sure that we put that athlete back onto the field of play with as robust qualities restored as possible. From here as well, this is obviously just the kinetics of what's happening. So we can use our coach's eye as well to understand what's happening perhaps kinematically. We know in ACLs particularly, there are some detrimental movement patterns that can remain for some time after return to play has occurred. So these are things that we can use both objectively using this kind of technology, but also layering that with the subjectivity of what we see with our coach's eye to get the best outcomes for the athlete. So knowing this, we can start to be a little bit more targeted and precise with the interventions to address the gaps that we see, which in this case, for this athlete, late acceleration transition. So this is the exact same run, and this is using our asymmetry portal on our web app currently. So again, when we're looking at phase level analysis, we've tagged left and right all the way through, which we do as we perform the run. And then what I've done as well is I've just taken a subset of those steps that we start to see where asymmetries really start to become more prominent. And we can see up on the chart there, it's happening at about step 7 and carrying through, honestly, throughout the entire rep, but really prominent from step 7 to step 14. So then what we can do on the software on the back end here is we can select a subset of steps. As we can see here, I've selected from 8 to 14. We can see our peak forces, step length, stride length, and frequency. And then this is up to you, but this is a left 16% asymmetry. Again, up to you if you look to act upon that or what you look to do with that. But we've got now the tools to be able to answer the question of where asymmetry, if at all, is occurring throughout that run. So then when we look at this same athlete, this is the same run. We can see that black line is the line or the trace we've been looking at for the last few slides, 3 kilograms, 30 meters. At the same session, this athlete also performed a heavier run, 15 kilograms across 20 meters. And what we can see is some very interesting changes between the lighter run and the heavier run. So now, what is the impact of external load on asymmetry? Well, as we saw earlier with Leo's run, when we add more load onto the resistance for resisted sprinting, it obviously closer resembles acceleration mechanics. So what we can see here is a 15 kilo run is keeping this athlete in more of an acceleration type mechanic, more acceleration style of run. And we can see the asymmetries are much, much smaller. Yet when we see, again, on that original curve, right at about 5 or 6 meters, when asymmetry starts to fall apart, we can start to see what those differences are and maybe start to link the different kinetic and kinematic demands of those phases to what we're seeing. So as we talked about earlier, acceleration much more anterior in nature, higher forces required, perhaps more correlated with more of your traditional metrics, knowing you're spending more time on the ground. And these are probably exercises that you're doing early in the RTP phase as well. It's something we're looking to restore in ACLs, obviously range of motion, muscle mass, but then we start to restore strength, whether that's a measurement isometrically on a Cybex. Strength is something that we would look to restore first and pretty early on. And we can see that this athlete's done a great job of that. We can see whether it's heavy accelerations with a heavy resistance or with a lighter resistance during that acceleration phase, we can see that that's been restored. But as soon as it gets up to more of an elastic, perhaps more of a vertical component requiring more stretch shorten cycle, we can see that perhaps is where we need to spend a bit more of our time. So all this to say, how does this enable us to be more targeted with our prescriptions? It helps us better bucket our athletes or better spend time in that rehab process. So far we've been looking almost exclusively at speed over position. Here we take a look at the horizontal force production. So effectively, how much force is that line being pulled on purely horizontally? And the story is the same. If we look at our lighter 3 kilogram run over 30 meters, we can see first few steps, very even, very smooth kind of peaks as we get to 5 or 6 meters. Then again, we see some very odd things starting to occur, even some bimodal curves from a force standpoint. But then when we look at the heavy red 15 kilo run, we can see, yes, there's some asymmetries there, but nowhere near as glaring as that lighter run. So when loading is introduced, how does that strategy change? Well, in this case, when we introduce load and it resembles more of an acceleration mechanics, we can see that she's quite proficient in that area. But when it gets to more transition max velocity sprinting, we can see that that's much more difficult for her to complete. So I might just pause there, Nick. Is there any questions on that before I dive into change of direction?
None in the chat, but we can open up here to the group if anyone wants to chime in.
Sure. All good.
I'll save my questions for the end, but we can keep moving. If you guys have any questions, again, we can throw them in the chat and revisit them as we go.
Perfect. I'll keep jumping in. So change of direction, something that I've spent a lot of time on lately. I think, again, with the strategy conversation of how the output's achieved, I think change of direction is one of those that we can dig into on a very granular level and get some really cool insights. So first of all, I just want to take 2 examples here of change of direction. On the left-hand side, we have an assisted start. So we're getting effectively towed into that change of direction. And with that, we get an unloaded acceleration. So that initial acceleration is going to be facilitated or unloaded, followed by a loaded or accentuated decel going into that cut, and then the loaded acceleration coming back out the other way. If we look on the right-hand side, we have a resisted start. So we have a loaded acceleration coming out. We have an unloaded decel. We come back to a loaded decel and then back out for a loaded acceleration, so on and so forth. So before we even dig into the data on the back of this, some of these tests can be manipulated and selected within the RTP process, especially to overload or achieve certain adaptations and certain stresses. For example, on the left-hand side, overloading the decel, obviously there's going to be a commensurate increase in soreness, increase in force output and demand, especially in the braking phase, obviously. But on the right-hand side, if we performed a resisted 505, for example, we're actually unloading that deceleration. So we can pull those levers during the RTP process to kind of achieve or still maintain the movement pattern and perform the movement pattern, but modify the loading around where those occur. So if we focus in now on just the 505, so what we saw previously on the left-hand side, an assisted start, we can see this athlete accelerates out of the blocks, 180-degree turn, and cuts back the other way. So we can see this is very easy to set up. We just set our 1080 about 5-6 meters away, set our 0 position, and go from there. Obviously, we can look at the different phases, which we'll get into, but also asymmetries left and right. But then again, also manipulate the acceleration and deceleration demands, knowing that with a 1080 sprint, you can modify the eccentric load independent of the concentric load. So we can tow someone in, for example, with 5, 6, 7 kilos, but when they change direction, we can knock all the load off of that back to 2 kilos if we want to, feel like they're getting shot out of a cannon. Vice versa, we can really drop the load down on the approach to 2 kilos, but as soon as they change direction, jack it up to 10 kilos. We have the options to be able to do that. And when I said break it down, this is kind of where we can go with it. So we have our 2 phases where we start from 0, we accelerate to a given top speed. We can look at our max acceleration. We can look at the max speed that we achieved, the maximum decel, meters per second squared, break down deceleration even more into decel time and decel distance. And then on that re-acceleration, the same thing. We can look at our acceleration in meters per second squared on the way back out, as well as the top speed achieved at the end of that repetition. So as I mentioned, the time is still the ultimate outcome. That's never changed. We're trying to perform these changes of direction as quickly as possible to close down a defender, to achieve possession of the ball, whatever we're trying to do, time is still the ultimate outcome. But what is the strategy that drives the outcome? That's where I think we can spend a little bit more of our time on the profiling side of things to answer that question. And before I dig into more of the modified 505, recent paper here published by a colleague of mine, Ola, with Adam as well, looking at a lot of different styles of 505s. They did pure ADAs, they did linear 505s, they did a lateral 505, like you can see here. So not only can we look at traditional tests like modified 505, we can start to look at vector analysis and consider different locomotive patterns dependent on what sport you're working with. So here is where I want to dig into a little bit around archetypes or different strategies for achieving high outputs in a 505, for example. So here, this is soccer data, professional soccer. We can see on our y-axis, we have the max acceleration in phase 1A, so that initial acceleration off the mark. And then on the x-axis, we have the top speed achieved in that phase 1A. All of this designed to determine that strategy that leads towards an effective and a fast 505. So we can see our color scheme that we have running here as well. Purple indicating lower times or faster times to complete the entire 505, closer to yellow and green, slower times. So automatically based on this chart, we can start to see now some of the most influential factors of these two metrics, what's influencing a really fast 505 time. And what we've come up with is kind of these different buckets. I love a quadrant plot. I think it just makes it really easy to kind of interpret the information. But we have floaters, flyers, coasters, and builders. And we'll get into these a little bit more right now. So flyers, athletes that have a really high acceleration off the mark, achieve a really high top speed going into that change of direction. They're obviously robust accelerators that are able to produce high braking forces because they're accelerating fast and also achieving a high top speed. These are typically your efficient and powerful athletes. And what that looks like when we look at our curves, this is directly from 1080 software, but we can see a nice, steep, robust acceleration as they accelerate off the mark, all the way up to a high top speed before they slam on those brakes and re-accelerate out back the other way. And this is kind of what we want to see when we're looking at that change of direction too. We want to see that really kind of narrow, steep V, where it's a really hard acceleration and a really hard deceleration as well. And you pair those together, that signifies a very robust or a fast 505. So we've touched on flyers, who are obviously robust and have very high quality metrics or high quality outputs, both acceleration wise and top speed wise. But what about everyone else? So if we look at the floaters, these are the athletes that have really high ability to accelerate, but poor top speed. So they're accelerating proficiently, but to a modest top speed, and then they quote unquote float until they're required to decelerate. So whether this is a kinetic limitation and they don't feel comfortable exceeding a given speed because they're eventually going to have to brake and apply large eccentric forces to brake their body mass, could be a regulating factor. Or it could be something related to the physical outputs or the actual eccentric force capacities that they have. And if we layer this on top of what a flyer looks like, we can really start to see, and this tells the story quite well, that both athletes have a robust acceleration out of the blocks, a nice and steep curve. But you can see these floaters, it kind of flattens out over the top here. And we can see, obviously, the robust acceleration, but then they kind of stop, float, and you see that somewhat of a plateau before slamming on the brakes. So that's what we would call a floater. If we go down to the bottom right now, we have builders, which is the opposite, effectively, of a floater. So poor acceleration, or more of like a delayed acceleration, but they're still achieving a high top speed. So for these athletes, you would expect quite high braking forces or high deceleration because they're accelerating late or accelerating not as steep as a floater or a flyer, but they're still achieving a high top speed. It's just happening later within that phase. And this is exactly what it would look like. So we can see that athlete has a delayed acceleration curve, yet still achieves a similar top speed. So we can see they're still having to slam on the brakes hard. We can see that there's a slight difference between the position there. So the difference in the distance of that change of direction. Obviously, the 1080 belt is being attached at the hip. So we can see if they're planting their foot perhaps I don't know, 30, 40, 50 centimeters outside the center of mass, touching the cone, turning and coming back. That's where we see slight differences in the total distance of that phase 1A, phase 1B as well. That's not something I'm concerned with, as long as they're performing that exercise as it should be. That is accelerating off the mark, going to the 5, and then coming back. And then lastly, we have coasters. This is not a bucket you want to be in. This is someone that does not have robust acceleration or top speed ability within this specific test. We can see the low top speed obviously decreases their ability or the requirement for high braking forces. Again, this could be a technical issue, or it could be something like underdeveloped physical qualities. So poor strength, poor power, poor execution, as I mentioned. And this is exactly what that would look like too. So we see that delayed acceleration, more of a flat curve, not quite as steep. We also see a less or lower top speed. Again, coasters, not somewhere you want to be. So now if we think about what do we actually do about this? So for a coaster, for example, but this could also be applied to other buckets within this framework, is we can look at some assisted lunges where we're using the 1080 in the gym. This could also be performed on the field, but we're really towing them in at 15 kilograms, single steps. We can go pure eccentric here with some assisted steps, again, towing in, all leading to the point where we can make it a little bit more ecologically valid, looking similar to what that first phase of a 505 would represent. So additional considerations, I obviously covered a modified 505, which is a very common assessment within the literature, very common throughout the country, throughout many different sports. But I think there's kind of been a bit of a shift as well in terms of how we can utilize perhaps GPS or other means to make our assessments more ecologically valid or better represent the demands of the game. So there's been a couple of papers here. Martin Boucher, he's kind of led the horse on that one. He's kind of assessed the demands using GPS and figured out in these specific papers that perhaps a 1505 better represents some of the pressing actions that you see in football. So then from there, using that to then carry over to the assessments, I think is just a really nice way to tie the demands of the game onto your assessments to kind of get a better representation of the capacities of your athletes relative to the sport that they're playing. Similar to how I showed the basketball lateral sliding 505, or just a pure lateral 505, we can kind of apply this. Again, this is from a colleague of mine, Ola. He put this locomotor framework together, but we have the starting position we need to consider, that initial acceleration to deceleration. What does that look like? Are we going forward? Are we going lateral? Is there any rotational elements? There's the transition. Are we doing a 180-degree change of direction? Are we backpedaling? What are we doing at the transition? And then the reacceleration. Again, what kind of movement pattern are we utilizing here? So I'll jump into some RTP applications here as well. I want to be cognizant of time, so I'll kind of get going on this one. So if we look at RTP and more specifically force diagnostics and how we can assess different components or different qualities, I think something that I found a lot of value in when it comes to implementing 1080 is the ability to assess across the entire force velocity spectrum. So with certain pieces, the quantum specifically, we can do supramaximal eccentric, so an eccentric boost function where that thing's coming down no matter what, and you're pushing against that eccentrically, obviously. We can do submax, eccentric overload, so applying perhaps a 20%, 10% eccentric overload on a given movement. As we shift into the concentric phase, we can look at isokinetics, and then we have obviously our normal functions as well of isotonic loading, and then all the way up to perhaps assisted loading as well when we're looking at overspeed training. So I think when we look at the categories here, we can not only assess and profile within these categories, but we can also prescribe to get very targeted with the desired adaptations we're looking to achieve. So here's Leo, once again, soccer player, pinged a hamstring, grade 1, so nothing major, but here he is performing an isokinetic, you could call it perhaps a supine hip extension, maybe not the best exercise for this specific injury, but this is a great video that I think demonstrates isokinetic loading quite effectively. One big thing, the elephant in the room here when we're talking about isokinetic loading and loading in general with the 1080 is there's moment arm considerations. Obviously on a Cybex, that fulcrum of the machine is aligned with the joint, so the moment arms remaining consistent, whereas here that's not the case. So there's obviously moment arm considerations that we have to take place. But that being said, we can start to get some really useful information. And this is obviously a hip dominant or a proximal hamstring exercise. And we can see on the right-hand side here the information we get on the back end when we look at left and right. Obviously the gray here we can see is his injured side, yellow being healthy side. We can see that upon that first kind of that force peak, it doesn't quite respond as high through the mid portion of the lift. And there is some form of degradation or some form of asymmetry, I should say, throughout that movement. And we can look at a number of different things. We can look at obviously the average force, I think is probably the best metric when we're using isokinetic loading. Peak force can be useful, range of motion, especially useful early on. And then of course, asymmetry as well. And within the 1080 software, this screenshot's directly from that, we can get all of those metrics on a rep level basis as well. So time under tension, the range of motion achieved, forces, power, obviously less so given that we're constraining velocity, but we can look at the average on the bottom right and also a quick snapshot of asymmetry. And when we talk about isokinetic loading, extremely potent, extremely powerful within the RTP process, given that it's heavily constrained. So we're constraining velocity, constraining position, setting the zero position on the machine. We can also constrain range of motion. And then whether you're pushing at a 2 out of 10 or a 10 out of 10, it's obviously moving the exact same pace. So we can utilize isokinetics throughout the entire RTP process. From the very first loading opportunity to return to play, we can perform the same exercise and use that as kind of a monitoring tool for how that tissue is responding to all of the other things it's being thrown at without having to, I guess, progress out of this. Now, we can obviously look at force over positions and times as well, and look at the speed over position and time. So where we use gym awares quite frequently in the industry, we can look at gym awares. We can also use that in a similar method as well, where we can look at the speed over the position of the movement, or we can look at speed over time. Again, all of these things that can kind of give you more information about how the tissue is responding across the entire range of motion. I'm an advocate for isometric loading. I think isometrics incredibly effective, especially early on, overcoming isometrics later on as well. But what we allowed us to do here, especially if we slow our isokinetics all the way down to 0.05 meters per second, so 5 centimeters or 2 inches a second, we can almost get close to what an isometric load would give us, but we're working through an entire range of motion, an incredibly potent stimulus as well throughout that RTP process. And here's a couple other options I always like to drop in for hamstring options specifically. If we look at more distal or knee dominant hamstring loading options, we have more of a stretched hamstring. So we're in hip flexion on the left-hand side here, 20 kilograms eccentrically coming in, 12 kilos concentrically. So this is a supramax exercise for this gentleman. Adding in some rotation as well, we can start to get more creative with how we load perhaps the medial and lateral compartments of the hamstring. This middle video here, we have an assisted single leg Nordic. So she's been provided just enough assistance to get through the range of motion, where we know that performing the entire range of motion in the Nordic, increasing fascicles that in series, those kinds of adaptations are advantageous. Being able to provide just enough assistance to perform that range of motion and maintain tension through the range of motion is a very useful application. And then lastly, we have on the right-hand side here, more of a prone hamstring curl. This is isokinetic. So we're working at 0.25 meters per second concentrically with very little, if not any, load on the eccentric. So again, the ability for us to vary or get creative with the hip, the knee positions, but also the loading type, whether it's eccentric overload, isotonic, isokinetic, we can be much, much more targeted with how we want to stimulate that target tissue. And not only in an RTP environment, but also with healthy athletes as well. Another example here of a rectus femoris strain, obviously more popular in soccer or in football globally, but more an example of more of a multi-joint type of exercise. And I want to highlight this here as we have our pulley system on the 1080 as well, where we double the line back. And what we enable that to do is we can increase the load capacity of the sprint machine from 20 kilograms concentrically up to 40 kilograms, and eccentrically from 30 up to 60. So if we want to do more high force work, not only again in RTP, but also with healthy athletes, we have that option to apply the pulley to kind of modify that loading a little bit. Now, I will say as well, when we double the load, basic physics, when we double the load and add a pulley, our speed is cut in half. So the max speed when we're using the pulley here is 7 meters per second, as opposed to 14 meters per second when there is no pulley involved. And just a couple other options as well that I think are useful to cover off here. So we have some projections, some first step exercises. Again, if we go back to our force velocity profiling, if we have someone who has a really poor F0 or poor RF max, that orientation metric showing how much horizontal force output there is, this could be something very useful. On the top right, we have more lateral based work. So he's getting pulled into that lateral bound with an eccentric overload and then shot out the other side. And then we have some deceleration steps here as well, something more overloaded on the left-hand side where you're getting towed in, and then even an unloaded, so kind of decreasing the amount of force required to push back out of it on the bottom right-hand side. More field-based. Some of our traditional tests and metrics, if we look at broad jumps, multiple broad jumps and hops, these are also things that we've seen a lot of people implement, just so we can get a little bit more granularity around the outputs and the strategy for achieving these different metrics. We get forces, we get speeds from these. With the unilateral triple hop test, I really like looking at the speeds and how those accumulate those takeoff velocities of those different jumps. So for me, it's really about, yes, the outcome is important, but how does that strategy change year on year, season on season, but also pre and post injury, obviously. And a couple more slides here just to talk through some tendon. I really think that, and we're back on isokinetic loading here, I really think that tendon, or the utilization of isokinetic loading for tendons, I think it's definitely an emerging field. There's definitely some research out there, but in the field, it's just not something you see as much, I think, given the restrictions around finding something that can provide isokinetic resistance. So I think generally speaking, people know nowadays tenocytes are relatively agnostic to contraction type. They like load. They don't really care if it's isometric, concentric, or eccentric. They just need load. Typically a strain magnitude of 4.5 to 6.5, based on what we know right now, seems optimal for adaptation. However, depending on the strength of the muscle, the stiffness of the tendon, and how that MTU kind of work together synergistically, high loads, generally speaking, are required to elicit that level of strain. So with that, we have a requirement for precise loading and for targeted loading to prescribe and monitor for tendons, knowing that it's very easy to overshoot and perhaps get a re-aggravation, or it's very easy to undershoot as well, to not squeeze out as much adaptation per rep, per session, per week, and so on, to make that tendon adapt. So this is where I think isokinetics, or more so constrained movement, affords that precision, because we're constraining the speed, which allows us to be a little bit more controlled of the stimulus. So we can see here, this is a basketball player, a Norwegian basketball player. On the right-hand side, we're doing a standing, on the right-hand side, we're doing a standing calf raise. This is at 0.05 meters per second. So again, very, very slow. But again, a slow speed allowing high forces allowing high strains on the tendon. And when we do this in a single leg fashion, I'll put a screenshot on the right-hand side there, we can see that there's significant decreases in the ability for that athlete to produce force on a symptomatic tendon. Range of motion seems relatively similar, but again, the ability not only from a peak, but also an average standpoint to produce force on that side definitely has some work to do. And we can see those are also seen in the seated version as well. So I pulled this from a recent session. This is updated just the other day, so forgive the glitchy Excel chart here. But I think a metric that we can use is mechanical work. So we're looking at the force multiplied by the displacement. So what's the average force of the repetition? What is the displacement? It gives us the work in kilojoules. So it gives us a way to objectively quantify the session load. Traditionally it may have been rep load or tonnage or impulse or something like this. I just think utilizing work accounts for the range of motion changes that you may see across that RTP process, especially when it comes to tendinopathies, where in an Achilles, for example, if there's some compressive elements involved, you may not want to get into extreme dorsiflexion. But as you get through that tendinopathy RTP, you're going to introduce more and more range. So I think this is where displacement factoring into the work calculation can be an incredibly useful tool to monitor that over time. And again, work agnostic to contraction speed as well. So if early in the RTP or throughout you want to drip feed some isotonic exercise, some eccentric overload, we can quantify those sessions in addition to the isokinetic sessions using work. And this is something I've been playing around with over the last month or so, a couple months, to better quantify the load that the system more so. It's hard to tell, obviously, how much the tendon is experiencing, but something that I've been using quite frequently to try and be a bit more objective with how we quantify, especially in tendinopathy cases. Perfect. And thank you for your time. I know I covered a lot there, so open to any and all questions.
Jesse, I had one on that last slide. Are you able to get that information in real time? Are you able to have like a feedback of the displacement and the force? And is that something that, you also utilize in session?
Yeah, so work, yes, work definitely. Displacement, I believe so. If not, definitely at the end of the rep. The end of the set. So in terms of live within the rep itself, I believe you have to wait till the end of the set. But this is certainly an area that I think is emerging. I haven't yet programmed based on work. It's more been something that I've kind of, done my normal sets, reps, loading progression, and then just kind of looked at what the work response is after that. And we can see here, I'm at 40 sessions. There's quite a nice kind of progression of cumulative work as we look at, that whole process over time.
Appreciate that. I think we have a couple more questions here. If anyone wants to share and unmute, more than welcome to. If not, I'll go to the chat here for a couple questions that we got. Well, I can start here from the chat. So Alex was talking about and asking regards to decel and change of direction training. He's mentioned having a lot of success manipulating entry distance and thus velocity as a progression. He said he typically only increases load and drops the entry distance back down once he's achieved a distance where peak decels level off. The question off of that is, do you have any other strategies or thresholds for when it is appropriate to increase load on change of direction tasks?
Oh, great question. I think first off, it's important to note that I recommend anyway, whenever we're doing any kind of overloaded deceleration, to not increase the load and the distance at the same time. It's usually one or the other. So we can either fix the distance and modify our approach load, or vice versa, or to basically manipulate the amount of impulse required to stop. We're manipulating that entry velocity, obviously, and then we're trying to create some sort of constraints around how much is required to stop. In terms of thresholds for how we should, progress, or how we should kind of select a ceiling, I don't have any absolutes in mind, if I'm being honest. But I think when it comes to deceleration, knowing that that has a higher risk for more adverse things to happen, I think you should definitely keep an eye on the mechanics of that as well. If we start to see perhaps loss of control as we get into that entry, that's probably a reason to be a little bit more conservative with the progressions. But great question. If you figure it out, let me know. But no, concrete rules yet around how we can set ceilings for deceleration training.
Yeah, it's a great question. I appreciate that insight too, Jesse. Another one here regarding force velocity profiling. The question is, are there standardized loads you use, or is this based on percent of body weight?
Great question as well. I recommend 3 kilograms across the board. And so what we also have written into the software is that you cannot get a force velocity profile if the load is above, I think it's 4 kilograms. because we want to replicate native sprinting as much as possible. As we kind of discussed, if you start loading them up 4, 5, 6, 10 kilograms, that's not really a representation of native sprinting. So the force velocity profile is going to be extremely erroneous. So we like to set a sweet spot of about 3 kilograms, which is enough, again, tension in the line, but also representative of what normal sprinting looks like to build that model.
And pivoting just a little bit, targeting eccentric overload, do you have a recommended ratio or zone for concentric speed versus eccentric speed?
Concentric speed versus eccentric speed. I think perhaps referring to load even, but for speeds, I mean, speeds, depending on what you're trying to achieve. Again, if it's an isokinetic, that's going to be slightly different. But if we talk about loads here, I usually start at, say, a 10% eccentric overload, which doesn't seem like much, but knowing that overloading that eccentric portion is where you're going to experience likely more soreness. There's going to be more neuromuscular damage. It's going to take a little bit more to recover from. I'm, again, much more likely to be a bit more conservative on that rather than aggressive, knowing that you can go from 10 to 15 to 20 within 2 or 3 sessions quite quickly.
And then the last one here we have in the chat is transitioning more to distance in the prescription with some of these interventions. So the question is 30 meter the sweet spot for distance in which you test, especially with lower loads?
Yes, is the short answer. I mean, the whole idea to test with lower loads is you want them to get to max speed. And most non-high level sprinters are going to get to max speed at 30 meters. You might have some, let's say you've got a football player or soccer player that previously ran track and they're quite technically sound. You may need to pull that out to 35 meters, but whether you're doing a force velocity profile or a load velocity profile, those are all incumbent on reaching max velocity. So 30 meters is relatively safe. 35 if you want to be absolutely sure. But again, 30 meters, 3 kilos, good to go.
And that's the final question. Any other questions here from the group before we wrap it up?
I'll throw
Jesse,
out
this
a
was
final
awesome, by the way.
question. Jesse, thank you so much. This was really good. When we were going over asymmetries on like the running shapes, some were bimodal, some were unimodal, and I think the bimodal ones were more problematic. What might lead to a bimodal curve?
Yeah, that's an excellent question. My suspicion or my hypothesis is that there is a significant lack or significant decrement in stretch shorten cycle performance of the Achilles calf complex on that involved side, such that there isn't that smooth energy return from that foot contact. That is my hypothesis. I don't have the data to back that up yet, but that is my hypothesis at this point. It's regardless as well of how or what it is effectively that's causing that. It's definitely not an efficient or a curve that I would feel comfortable returning an athlete to play with. That's for sure.
Gotcha. Yeah, that makes sense because I think like with force plate monitoring too, you see like the bimodal and unimodal curves as well. But then yeah, like the reasoning for it might vary between individuals. And then we have a last minute question in the chat from Shane.
Sure.
Can you conduct a load velocity profile test or force velocity profile test on swimmers? And if so, how would you recommend determining loading parameters?
Yes, it is becoming a much more emerging field for us. We are having more and more swimming clients reaching out to us, but also utilizing the technology. There's a really awesome paper out of I think it's the Irish Swimming Federation that go over pretty much their whole year of training for an Olympic level sprint swimmer that encompasses their load velocity profile. And if I'm not mistaken, I believe they created their LVP using 1, 3, 5, and 7 kilograms, I want to say. But again, that paper is out there. I can share that in some capacity if you wish, but it's not too hard to find, and it's an excellent paper.
Awesome. Well, thank you so much. I just want to be mindful of everyone's time. Jesse, thank you for your time, insight, for all of this. Before we wrap this up, I just wanted to thank everyone for being here. We really appreciate you taking the time to join us. And Nick and I also have some really exciting news we wanted to share with everyone. Because of your support, our CPSS prep course is now officially the NSCA authorized learning resource. This has been something that Nick and I have been working on behind the scenes for a while, so it's really great to see this come to fruition. This is a huge milestone for us, and it honestly wouldn't have been able to happen without all of you, everyone who's taken the course, supported us, shared what we're building. So thank you all so much for supporting us. There's a QR code in that figure too. If you want to scan it, it'll bring you straight there. And then that'll wrap it up. Thank you all so much for being here and have a great evening.
Thank you, everyone.
Thanks again.